Okay. Let's get started. Of course, I will have to go back to a few slides on breadth first search that I didn't get to do last week, and I will do that at the beginning of today's lecture. But before I'm going to do that, because I guess this is very important, let me start with a few comments on what's going to happen next week before the lecture next week. As you would have seen, and as you know, we will have the midterm online test next week between Monday and Tuesday. What should you do to prepare for it? You should review all the concepts that we went through, all the data structures that we looked at, and all the algorithms from weeks 2 to 7, including what we will be talking about today. Everything can and will be included in the midterm test. The programming assignment was focusing a lot, obviously, on the introduction to C and data structures and memory allocation in C. So the focus for the midterm test will then be on the second half of the first half of this lecture, that is analysis of algorithms and graphs. But there will also be questions about the first half, so everything can be included in the mid-session test. Now, obviously, when you do that at your own time and at home, you can look at all the material while you do the test, but it's still a good idea to prepare for the test by reviewing all the concepts, data structures, and algorithms. Only then will you be able to answer the questions in time. What we will do in this lecture is we will be looking at more graph algorithms, circuits, and reachability in directed graphs. I will, at the very end, give you a demo of a mock quiz on Moodle, which I first of all show you so that you know what you can expect for the midterm online test. The environment will be exactly the same, so you will see how these tests look like. And this mock test will contain 3 questions, which you can then also try yourself, because these questions are indicative of the type of questions that you can expect for the actual test. Also, at the very end, I will have an in-class fun quiz where you can win fame and prizes. And the purpose there is also to just show you a few questions, in this case multiple choice questions, in preparation of the midterm exam, or midterm test, I should say. Coming up, more graph algorithms. We will complete the introduction to graph algorithms next week with looking at spanning trees, minimal paths, and so-called network flows. Now, a few words right now about the midterm test. Can I get everyone's attention for this? You should be doing it between Monday 12 noon and Tuesday 12 noon, or here I put 11:59 just to make clear that it ends on Tuesday. You have in total 1 hour. There will be 10 questions, and they have been designed so that you should, on average, need no more than 5 minutes per question. So the mid-session exam actually, or mid-session test, is timed for 50 minutes, and I give you in total 1 hour, so that if you experience any network issues and you have to log out and log onto, that you've got this additional 10 minutes leeway to account for all of this. There will be 10 questions. Each question will be worth either 1 mark or 2 marks. 5 are worth 1 mark, 5 are worth 2 marks. The maximum marks is 15. It will be a mix of multiple choice questions. The multiple choice questions can have more than 1 correct answer, and we will see in the mock quiz how that works. But there will also be questions with open answers, numerical answer, and short text answer. And again, the mock quiz that I will show you at the end of today's lecture illustrates all 3 of these categories. So that mock test is available on Moodle to practice. I will show it to you, but you can then log on to Moodle yourself and practice the test yourself. Now, very importantly, this is just like a regular exam. It might very well be the case that you are, when you read a question, you're uncertain about how to interpret it, or you're unsure about how to answer a question. Or it might very well be that you find a question too difficult. This is perfectly normal. There are simple questions, and there are difficult questions, and there might even be one that is really, really difficult. So not everyone is expected to be able to answer all these questions. If that happens, and you don't really know what I want from you or what the question is asking from you, just try to answer to the best of your understanding. First, what you should do is, of course, focus on the questions that you find easier and where you think you know exactly what you're being asked about. And my last advice is do not agonize about a question if you really don't understand it or you really find it too difficult. And don't agonize about your answer after you've submitted. The test will be open for 24 hours. And at the closing, Tuesday noon, you will get feedback and your result through that auto-marking. Not before, so at some point you will submit and you don't know what's going to happen until Tuesday. Just be patient, don't agonize about anything. Remember that this test is worth only 15 marks. And it is mostly for you to see whether you are able to answer simpler or more difficult questions about the contents that we have discussed in this course so far. Now, obviously, I can't check whether it is you yourself who is answering these questions, but it's mostly for you to know where you are in this course here. So do it yourself, but don't agonize about not being able to answer all questions. I apologize in advance for the next slide, but on experience, I mean, it's common sense, but nonetheless, I just want to make it very clear that the purpose of the test is everyone does it themselves, everyone does it at different times, and it just makes no sense and would be totally unfair if anyone who has already done the test, let's say on Monday, would ask any question on the forum. So the strict rule is absolutely no posting on the forum on any topic while the test is up and running between Monday noon and Tuesday noon. So don't post any questions after the test has officially started, even if you haven't started yet, because other people might have already started and they might even have finished the test. Don't ask any question during the attempt. And also, very importantly, don't ask any questions after the attempt. You might think that you have finished, but there are still people out there who want to do the test and who will do the test. So I can't possibly answer any questions, and just to make that very clear, within these 24 hours, no posts will be answered. They will all be deleted, and posting will be penalized. We receive emails as soon as a post appears, and therefore don't use the public forum at all, please. If you have serious concerns about your test, don't use the public forum, just email us.
With the questions,
yes?
are you like the whole 10 all at once, or do you have to submit one and then it goes on to the
Just wait for the mock test in the end, where I will show it to you, but the answer is no. You can go back and forth, navigate between these questions, and then go back to the more difficult questions later. But really just wait until the end of this lecture. Okay, so much for this. Now let me quickly go back to last week, where we introduced graphs and several ways of representing graphs on a computer. And then we started looking at our first algorithm, namely depth-first search. And we will also now be looking at breadth-first search. Just remember depth-first search. This was the one example that we looked at. We wanted to find a path from 0 to 6. And depth-first search now proceeds as follows. If we visit neighbors in ascending order, we go from 0 to 1 to 5, 3, then 2, always choosing the vertex that is, has the smallest index over all those that can be reached. Now from 2, we don't continue because we've already visited 0. So we go back to 3, then 4, 7, 8, 9, and then we are stuck. We can't continue from here, going to unvisited vertices. So we backtrack 8, 7, 4. There's no choice here because we've already visited 5. So we ultimately go back to 5, and then we find 6. Now that doesn't give us the shortest path. As you see, the actual path that is being computed is 0, 1, 5, 6, whereas 0, 5, 6 is a shorter path. And we will use breadth-first search because that enables us to find shortest paths. Before we do that, let me mention, in preparation of breadth-first search, that depth-first search, we have described it recursively so far, but it can also be described non-recursively with the help of a stack. The idea of using a stack would be that you put all the nodes where you have alternatives onto a stack, and we'll come back to that stack element later when you have exhausted all other possibilities. So in this case, you would start with putting 0 on the stack, pop it, and look at all the neighbors. There are 3 neighbors, 1, 2, and 5. You would put all of them on the stack. 1, 2, and 5 are 3 choices. And then you would continue with the top element. Say this is 1, if we make sure that we do that in ascending order. And then from 1, you would put the vertices that can be reached from here onto the stack, which would be 5. And because you always put elements on top of the stack, this does model depth-first search, because you would always choose the next alternative that you've just pushed onto the stack to continue searching. And this results in this algorithm, depth-first search using a stack, where you want to find a path from source to destination. You begin by pushing the source onto a new stack as the one and only element. And then you have a while loop while you haven't found your destination. And as is not empty, that is, you still have alternatives to search through, then you pop the latest element from the stack. You mark it as visited to make sure that you don't run in circles. And if you have just popped the destination, you know that you've found your path. Otherwise, you consider all the edges from the vertex that you've just popped off the stack, so that W has not yet been visited, and you push that onto the stack. It's exactly the same algorithm. It uses the standard stack operations, push, pop, and checking if a stack is empty. And the time complexity is also the same. In the worst case, you have to visit each vertex by adding it to the stack. And each vertex adjacency list is visited once when you go through all the edges, as I have marked here. Now let's look at this as a quick example to see how the stack evolves and to understand that this is exactly the same algorithm, well, not the same algorithm, but the same method as the one that we had with a recursive definition. Now here we want to find a path from 0 to 5. So source is 0, destination is 5. And according to the algorithm, we have to, first of all, take the source and push it onto the stack. This is what happens first. The source is 0, so our stack starts with just having 0. Now we pop 0 off the stack. This is our first node to begin with. And, sorry? Yes, so that is one thing that is being said here. In order to make sure that we follow nodes in ascending order, you have to push them in descending order, making sure that the lowest, the node with the lowest index ends on top. Now, how many different neighbors do we have of 0? It's 5, 4, and 1. And all 3 neighbors, if we go through all the edges from 0, they are pushed on the stack. And we do it in this descending order. 5, 4, and 1, to make sure that when we continue by popping the top element, we continue with the element with the lowest, the vertex with the lowest key, which in this case is 1. So this is where we are. Then we pop 1, which means we have 5 and 4 here. And we push all the elements on the stack that are reachable from 1. Now this is in principle 0 and 2, but we don't push 0 because 0 has already been visited. And the algorithm here says only take visited, non-visited nodes. This is what it says here. W has not been visited. So the only other node that is now added is 2. Then from 2, we see we can't push 1 because we've already visited 1, but we haven't visited 3 or 4. And this is why when we take off 2 and consider all the neighbors of 2, we push 3 and 4 in reverse order. Push 4 first and then 3. 5, 4, 4, 3. Now you see that element 4 actually appears twice on the stack, but this is just the way this algorithm has been defined. It says that a vertex is marked as visited only after it has been popped off the stack, and 5 and 4 have not been popped off the stack. The reason for me having written this algorithm in this way is that this is precisely what the recursive algorithm also would do. It would, when it wants to go to 4, it would really go 0, 1, 2, 3, 4, and would not go to 4 directly. If you had marked 4 as visited already, then you wouldn't be able to get to 4 in the way that the recursive depth-first search does. So then we've got 3 on top. We take that off as the first element, continue with 4 and 5, and that gives us, we have 5, 4, 4. We still haven't seen 5 and 4, so we put 5 and 4 on top. This is exactly right, 5 and 4. And then popping off 4, the only reachable vertex now that is 5 that hasn't been visited. We have visited 0, 1, 2, 3, but we haven't visited 5, so we push 5, 5, 4, 4, 5. And then finally we pop 5, and this is the vertex that we were looking for. And then you can see if you follow the path that we took here, this is exactly the path that we would have found with our recursive depth-first search. So this is how the depth-first search with the help of a stack works. And one of the reasons to look at this is that we've seen that here. This is exactly how the stack evolves, as we have just seen. And the reason for looking at the stack implementation is because it gives us a very nice implementation of the breadth-first search. The basic approach to breadth-first search, remember, was to visit and mark a current vertex, then to visit all neighbors of the current vertex, all of them, before you then go on to consider neighbors of neighbors. This, unlike depth-first search, is a bit tricky to describe recursively, but it is very nice and convenient to describe it with the help of the same kind of algorithm that we just used for depth-first search, but switching the stack for a queue so that the newest element don't come on top of the stack, but they go to the end of the queue. And in this way, as we will see, we make sure that we visit vertices in the way that we want to visit them when we want to do a breadth-first search. So here's the algorithm. This algorithm also keeps track of the visiting order so that in the end we can recover the path that we have found in the same way we have done when we rewrote the basic depth-first recursive search algorithm. And what I'm also doing here is that we mark vertices as visited when they are put on the queue and not when they are taken off the queue. That avoids what we just saw, that we put multiple nodes or the same node multiple times on the stack. If we mark it not as before when we take them off, but mark them as visited already when we put them on, then we can avoid this. So this is exactly the same algorithm as we've just seen, except that we are now using standard queuing functions. We use the source as the first element in the queue, while the queue is not empty, we dequeue a vertex from the queue. If we have found the destination, then we have found our path. Otherwise, we go through all the edges outgoing from V that haven't been visited so far. So that visited W, which we've initialized as -1, we have done that up here. If they haven't been visited yet, then we put them at the end of the queue, and at the same time we mark them as visited. And we do that in such a way that we use that visited array and assign the predecessor, V, where we just came from, to that array in order for us to be able to recover the path in the end when the algorithm terminates. Well, that works exactly like the depth-first search with the stack. Now here with the queue, we use standard queue operations, adding an element to a queue, taking an element off the queue, and checking whether the queue is empty. Now let's see how that works with our example that we have already seen for depth-first search, and where we saw that we end up with a path, but we didn't necessarily end up with the shortest path. So now the task is to apply this algorithm, but using a queue instead of a stack, and therefore applying breadth-first search. All right, so this is the graph, and all these question marks, we initialize the visited array with -1. This is what the question mark should indicate. Then our task again is to find a path from 0 to 6. So according to the algorithm, the first thing after we've initialized the visited array is to take our source node and put it into the queue, which would be 0. We also say visited source is source. That is, we can put in the 0 here to mark the end of the path if that is necessary. Okay, now just like with the stack, we take the element, in this case the only element, and take it off the queue. And now we add all the neighbors of 0 to the queue. These are the ones that we can visit next. This would be 1, 2, and 5. And unlike with a stack, we don't have to process them in reverse order to get the order right, because we would always go from front to end. So we would first of all enqueue 1, then 2, and then 5. And this is what happens in the next step. This is now our queue. We have just enqueued 5 as the last element, and now we go back to the first element when we dequeue the next vertex to continue with. What we also do is, as we enqueue these elements, we have said we want to mark where we came from. We want to mark them as visited. And that means we put in a 0 here, a 0 here, and a 0 here. This is the source node where we would have come from for all 3 elements. So then what happens next? We take 1 off, yep, and that's exactly right. So there isn't really anything that we can do with 1 because we've already visited 0 and we've already visited 5. So that node is simply ignored. In other words, this for loop here is empty. It doesn't even run. And this is to make sure that we go, for example, when we want to visit 5, that we go directly from 0 to 5 and not via 1. So we take 1 off, nothing happens there. We continue with 2. And 2 has 2 neighbors, 1 and 3, or 0 and 3. We've already visited 0, but we haven't visited 3 yet. So we can put in 2 here. This is where we just came from. And we add 3 at the end of the queue. Our next vertex at the front is 5. And from 5, we have several possibilities. 0, we've been there. 1, we've been there. 3, we have been there. But we haven't seen 4. Let's add it. And we haven't seen 6. And we haven't seen 7. So 3, 4, 6, and 7 will be added. And that means, whoops. No, 4, 6, and 7 have been added from 5. So we put in 5 here, 5 here, and 5 here. Okay, almost there. Next vertex is 3. The only vertex we haven't visited from 3, the neighbor is 8. So that comes at the end, and we put in a 3 here. Very good. 4. Well, there's nothing there. 3, 5, 7, and 8. All the neighbors of 4 we have already marked as visited. So we end up with dequeuing 6. And dequeuing 6 is exactly what we were hoping to do at some point, because that is our destination. So we are now here. We have dequeued the destination, and we have found our path. What is the path? 6, 5, 0. So if we display the path in reverse order, from 6 to 6, we came from 5. From 4 to 5, we came from 0. And this is why we have 6, 5, 0. And you can see now this is actually the shortest path, unlike the depth first search, which gave us the path 0, 1, 5, 6. Here we have found the shortest path with the help of our breadth first search. So that's how this algorithm works with the help of a queue. And if you've done the homework for last week, then you would have seen that exercise number 5 was concerned with breadth first search and depth first search using queues and stacks. Since I haven't talked about this, I didn't expect you to look at these questions just yet, which is why I haven't published any solutions just yet. But I will publish the solutions this Friday, which I will also do with the problem set for this week, just in order that you get prepared for the mid-session test next week. And this, as I said, this one exercise allows you to exercise your understanding of how the stack and the queue evolves when you do depth first and breadth first search. So that we just did. This is the results, and indeed the only node that we never visited was 9. The path that we in the end computed was 0, 5, 6. Time complexity is, if you use an adjacency list representation, exactly the same as depth first search. The advantage of breadth first search is that it finds the shortest path. If we define shortest as the smallest or the fewest number of edges between source and destination. It stops with the first found path. If there are multiple ones, then breadth first search will just stop once you have found the destination that you were looking for. I should mention that in many applications, when we talk about shortest paths, like on Google Maps, then edges are weighted, and we are actually looking for a path that is based on the minimum sum of weights along a path between source and destination. So we wouldn't just count the number of segments, but we would take into account how long these segments are or how fast you can travel on an individual segment. We will discuss that not today, but next week when we look at weighted and also directed graphs. I've already talked about this, and that concludes the introduction to graphs from last week. We've introduced a number of concepts, simple concepts, such as vertex degrees, connected graphs, trees, paths, and cycles. They are all mentioned here. And as usual, when I mention things on the summary slide, these are the things that you really should know. Graph representations, we looked at 3 different representations. We've focused on the implementation using an adjacency matrix. And we looked at the first graph algorithms, depth-first search and breadth-first search. Okay, and now with this, we can move on to further graph algorithms. Before we do that, let me quickly have another look into my DAO of programming, which has another interesting advice concerned with what you should do when you write more complicated algorithms or more complicated programs. In book 3, chapter 3.2, you can read that there once was a master programmer who wrote unstructured programs. A novice seeking to imitate him also began to write unstructured programs. When the novice asked the master to evaluate the progress, however, the master criticized the student for writing unstructured programs, saying, what is appropriate for the master is not appropriate for the novice. You must understand DAO before transcending structure. Why am I saying this? It is really important to write structured programs, simply because it's much easier to understand, much easier to maintain, and much easier to communicate. So even when you see people writing unstructured programs and trying to squeeze everything out of the syntax that C allows you to make it as short as possible, these programs then tend to be harder and harder, get harder and harder to understand, and it is just not a good idea. Unless you're a real expert in this programming language. But even then, it's not a good idea if you want to pass on your program to someone else. So that as a warning, when we now look at more interesting graph algorithms, there are heaps of, generally speaking, problems on graphs that people solve for many different applications. And here's just a very small number of those. Is a graph fully connected? Can we remove an edge and have the graph still fully connected? Is one vertex reachable from some other vertex? We already looked at depth-first and breadth-first search to answer a question like this. What is the cheapest cost path from V to W is what Google Maps always does for us. Which vertices are reachable from V, which is known as transitive closure? Is there a cycle that passes through all vertices or all edges? We will look at that question today. Is there a tree that links all vertices, which we called a spanning tree? What is the minimum spanning tree? That has lots of applications, and we will be looking at minimum spanning trees next week. What is the maximal flow through a graph? We will define that next week when we look at graphs interpreted as flow networks, where you want to send something through the edges of a graph from one node to another, and you want to maximize the throughput. Other questions that we won't be considering here are also very important. Can a graph drawn in a plane with no crossing edges, also known as planar graphs, or are two graphs somehow equivalent, graph isomorphisms? All these and many, many more questions can be of interest with graphs. What we will be looking at is algorithms for connectivity, simple graphs like we have looked at so far, path finding, that we have already looked at, but we will be looking at directed graphs and what we can use there, and finding shortest paths with weights. We will be looking at minimum spanning trees, shortest path with weighted graphs, as I just said, and maximum flow in flow networks with weighted graphs. We already looked at depth-first and breadth-first traversal, and we will now be looking at how we can use the idea of these traversals, in particular depth-first search, to solve other problems. In particular, you can use depth-first search to check whether a graph has a cycle or not, and determine which connected component each vertex in a graph is in. If you look at this graph as a whole, which has 8 nodes, then you can see there are 2 connected components. The vertices here are somehow connected, and the vertices here are connected. And we can determine which of these 2 connected components each vertex belongs to with the help of depth-first search. Also, we can use depth-first search to detect a cycle like this. Now, the idea to detect a cycle with depth-first search is actually quite simple. You use DFS, starting at a randomly chosen vertex, and then you go deeper and deeper into the graph. And if you then come back to a node that you have already visited, then you have found a cycle. So that's the idea of a cycle check, which is implemented here with this algorithm that, however, has two bugs and doesn't work. It implements that idea, but doesn't work exactly as we expected. And I will ask you in a minute what is missing in this algorithm so that it doesn't actually work correctly for all graphs. Now, to remind you, a graph has a cycle if we can find a path of length greater than 1, where we start with the vertex source and we end with the exact same vertex. So the starting vertex source is the same as the end vertex destination. Think of that triangle. It's a very simple example of a cycle, and without using any edge more than once, which we do in our triangle. Now, cycle checks, we will use them later for other graph algorithms. They are really important. For some of the methods that we will be looking at, you're typically not interested in finding a cycle. You just want an answer to the question, is there a cycle or is there no cycle? So here we have an algorithm that either returns true or false, depending on whether we can find a cycle or not, with the help of depth-first search. The input is a graph. The output should be true or false. And we use the recursive depth-first search by randomly choosing an arbitrary vertex and starting from this vertex with our depth-first search. Now, the depth-first search works as follows. We mark the vertex as visited. Then we look at all the edges, outgoing, all the neighbors W. If W has been visited, then we have found a cycle. We went back to a node that we have already visited, and therefore we return true. If W has not been visited, then we continue recursively to do the depth-first cycle check. So think of the triangle. You start here, you go there, then you go to this vertex, and then you go back to the vertex that you started with. Then if the recursive search returns true, eventually we go back to a visited vertex, then the answer will be true. And only if we can't possibly find or go back to any visited vertex by doing this, then this algorithm returns false. Sounds all very natural and doable and feasible, but there are two problems with that algorithm. Can anyone see either of these two problems?
Check if the first enter the connected element of the graph.
Components, yes, that's a very good observation. We choose any vertex whatsoever, and if that vertex belongs to a component that doesn't have a cycle, suppose we don't have that. I mean, this has a cycle as well, this triangle, but suppose there was no edge between 0 and 3. Then we would, by depth-first search, only consider all the vertices that we have here. And we would say, no, there's no cycle here. But we wouldn't detect this cycle here. Because using depth-first search, we will never be able to come from this component to this component. Very good observation. So that doesn't work because it doesn't check all components. It checks only one component, depending on which vertex we chose to begin with. First bug. And the second bug, maybe someone else. Yes? That is correct, indeed. The for loop is a bit too simple because it says for each edge that you can go to, if W has been visited. Now, if you start at one vertex, you go to the next vertex with the help of one edge. Then from the next vertex, you can actually go back to the first vertex. And this has already been visited. In order to find a cycle, this is not allowed. To have a cycle, you have to go to a third vertex first and then go back to the first one. So indeed, this is the second problem. This would recognize or find a cycle in almost every graph. As soon as you have one edge in the graph, it would say it has a cycle. And you have to avoid that as well. So indeed, only one connected component is checked. And secondly, the loop that we used should exclude the neighbor that we just came from, so as to prevent just one single edge be identified as a cycle. Now, I'm not going to correct that algorithm here. I leave that to you as one of the exercises for this week's problem set. Shouldn't be too difficult if you take this algorithm and just take into account these two bugs and improve the algorithm in that regard, then you would have a correct depth-first search-based cycle check. Speaking of components, let's look at the other problem. The problem that might also be very interesting. When you have an arbitrary graph, you want to answer the question how many connected subgraphs are in the graph. And you may want to answer the question whether two vertices are in the same connected subgraph, in which case you immediately know that one can be reached from the other. You don't have to search for a path. You just know they belong to the same connected component. And therefore, yes, there must be a path from A to B. Both can be solved if we can build an array which contains one element for each vertex, indicating which component the vertex belongs to. And for this purpose, I'm going to use an array called component of, which for every vertex gives us an ID that just numbers the individual components. Now, here is an algorithm that does this and also uses depth-first search to do this. The idea, again, is relatively simple. You, first of all, say that, well, we haven't labeled any of the vertices to begin with. They all get the component -1, indicating that they haven't been visited. And then we use a component ID, initialized as 0, which will then be incremented once we need to go to a new component. So if our graph has 3 components, then in the end we want to use component IDs 0, 1, and 2. And all the nodes in the first component will get component ID 0, all the nodes in the second component ID 1, and third component ID 2. So how do we do that? We look at all the vertices in the graph. And if we have a vertex that doesn't have a component assigned just yet, then we do a depth-first search from that component, from that vertex, with our current component ID. And once we've done that exhaustive depth-first search, we know that we have searched for all the elements that are somehow connected to V, so that we now move to the next component ID. Let me illustrate that with this example that we had here. We start with an arbitrary random vertex. If we do that systematically, we would probably start with just the lowest index 0 here. Then we would use depth-first search to label all the nodes that can be reached from 0. And once we've finished with that component, we would go through all the unlabeled vertices. The first one we would find is probably this 4 here. And then we would do another depth-first search here, label all these with the next component ID. And in this way, we label all vertices with an ID for the component that they correspond or belong to. And the depth-first component search with a particular ID is very straightforward. We take our vertex that we start our depth-first search from, assign it the ID of that component, and we look at all the vertices adjacent to V. If they haven't been labeled just yet, why is that important? Because we have to make sure that we don't run into cycles. If we go back to a vertex in the same component, then it already has been labeled with that component ID and we can ignore it. We do the depth-first search from there. And this is all we need for this particular problem. Let's just see with a very simple example how that would label all the components that we have here in that graph. Now, at the beginning, all the vertices are not labeled yet. They get the component of ID of -1. And then in the algorithm, it says we start with component ID 0. And then we have to go through all these vertices. If we do that in the order in which they are numbered here, we would start with 0, assign component ID 0 to it, and look at all the neighbors, or rather, as the depth first search, we would choose the next neighbor and continue with that next neighbor. So we take the vertices adjacent to V that haven't been labeled yet and would continue our depth first search recursively, which means that the next vertex would be labeled with that component ID as well. So we do have, let me make sure that I'm solving the right problem. So I want to solve the problem without the dotted edges. That means this edge here that is indicated is not actually part of that first question. So the only choice that I have is to go to 2. I mark this with 0 and then go to 1. I mark this with 0. I can't go back to 2 because this has already been marked. 2 has already been, I couldn't go back to 0 because it has already been marked. So I'm actually done with that component. The recursive call, depth first components, terminates at this point. And that means I go back to the main loop here. And it actually means that I increment the component ID. So I've now used 0, and I increase that to 1. And continue to go through all these vertices. Now, if I do that systematically, then I did start at 0. And the next vertex to consider would be 1. Now, 1 has already been marked, so I don't do anything with 1. The next one would be 2. 2 has already been marked. So I would go to 3. Now 3 has not been marked, so I do start my depth first search with the new component ID at 3. And that obviously gets me to 4. Will also be marked with 1, and that terminates that second call to the depth first search. The component ID is incremented further to 2. And clearly this gets 2, this gets 2, this gets 2, and there's nothing else that needs to be done here. And when I then come back from the recursive call, which I've started with vertex 5, the only 2 vertices that I haven't looked at in the outer loop, that is in this loop of the component's main function, are 6 and 7, but 6 and 7 obviously have been labeled already, so that the algorithm terminates. And it does give me the labeling of all the components. What would change if I were to add these dotted lines? Well, first of all, when I go from 0 to 2 to 1, I would have the neighbor 0 to consider, but it has already been labeled, so that wouldn't change anything. But then from 2, I still have that alternative to go to 3, and that then would also be labeled with 0, and the depth first search would be going also to vertex 4. They all then belong to the same component, whereas 5, 6, and 7, for this I would have to start a new depth first search, and they then obviously would get the component ID 1. So with the dotted edges added, the answer would be 1, 1, 1 here. All right, so that was 2 further applications of depth-first search. Depth-first search we will continue to be using for more algorithms. It's one of the really basic fundamental techniques. For some cases, we will actually need breadth-first search as more appropriate, but we will see that later when we come to these problems that we have just done. And this is the actual result that goes through the graph step by step and shows you how the component IDs are being updated in the first case and in the second case. And you see in the first case we have 3 components. In the second case we have just 2 components. Now let's look at a different type of problems where we will actually see that depth-first search again comes in handy and provides us with a nice solution to at least one of these 2 problems. We'll now be looking at what is known as Hamiltonian and Euler paths. Now these 2 types of concepts, they require you to visit, in case of a Hamiltonian path, all the vertices of a graph without going back to any vertex twice. And in the case of Euler graphs, we will be looking at using all the edges exactly once. Now let's look at Hamiltonian path problems, which has a variety of applications that I'm mentioning here on that slide as well. The definition, some of you might already know this if you have attended my Introduction to Computer Science last semester. But for everyone else, Hamiltonian path problem means to find a simple path that doesn't revisit any vertices, that connects 2 vertices, V and W, in a graph, so that the path includes each vertex exactly once. Not more than once, but you're also not missing a vertex. You really have to visit all the places, all the nodes in the graph. This is the path, Hamiltonian path problem. If you want to come back to the node that you started with, then this is the only exception. It is officially allowed to visit one node twice, namely the starting node. And if you can do this, then we say that we have a Hamiltonian circuit. Now there are graphs that have a Hamiltonian path, but not a Hamiltonian circuit. But obviously, if you have a Hamiltonian circuit, then you can stop at the penultimate node, and that would give you a Hamiltonian path. So circuit is a stronger condition, existence of a circuit, than a simple path. Now, what's quite interesting about this problem is that it is nice and easy to state, but it is difficult to solve. Is there any question? Any question? So it's a bit like the subset sum problem that we looked at. This question to find a Hamiltonian path is also known as one of the hardest problems, so-called NP-complete problems. And again, if you fail to find a polynomial algorithm for subset sum, but you're able to find a polynomial algorithm to solve this problem, then you will win fame and money, and you would have solved one of the most important problems in computer science. But no one has yet found a non-exponential algorithm that works for all the graphs. But I'm just waiting for one student. Kai, is he here? Kai?
Yes.
Was it you?
Yes.
Who had ideas for how to solve the subset sum?
Impossible.
It didn't really work, but maybe you find one for the Hamiltonian path problem. And then tell the world that I've been your teacher. Okay, so applications of this are a very famous problem, traveling salesman. The idea of a traveling salesman is the traveling salesman wants to visit every city, but only once. Bus routes are also an important problem. You want to visit or to drive to every particular stop along a route, and so on. So going through all the nodes, but not visiting a node twice. The problem, by the way, is named after an Irish mathematician, physicist, and astronomer by the name of Sir William Rowan Hamilton. This is where the name comes from. So let's look at just a very simple example. We have a graph, and we want to find a Hamiltonian path. You can see that there are actually several paths. Even if we say that we want to go from 0 to 3, there is more than one possibility. We can go 0, 1, 2, 3. Oh, actually, this is the only way to get to 3. But to get from 0 to 2, it's very easy. We can either go from the 0 to 3 to 2 or from 0 to 1 to 2. And this is also a possible path that we have here. We have enough edges so that this is really very simple to find a Hamiltonian path in this graph. But there are other graphs where this is fairly difficult. And rather than doing this by hand, here is an approach that allows us to answer the question. The basic idea is that we generate all possible simple paths that don't go through cycles, using, for example, depth-first search. We have seen that DFS is a nice method to do this. We do keep a counter of vertices visited in the current path, and that we do so that we can be sure that in the end we have visited every path. Because if we have, if our counter increases and in the end we have exactly v vertices visited, then we know we have visited all the vertices. And we can say that with confidence because we don't go into cycles. That is, with depth-first search, when you have reached a depth of v, then you know that you have visited all the vertices. So that can be expressed via a standard recursive depth-first search algorithm, which is very similar, identical even, to simple path finding, except that we keep a counter to keep track of the path length. And we succeed not if we have found a destination, because it doesn't really matter where we end. We only want to make sure that we have reached the destination, so that we have reached a destination with the maximal length, which is the number of vertices. And of course, we have to reset the visited marker after an unsuccessful path. So this is the algorithm here. And right after that, we will see another example, and I will take you through that algorithm step by step. So we keep our visited array. The question is, do we have a graph that has a Hamiltonian path? Here we say that we want to have a particular Hamiltonian path from source to destination. And you can do that with this source and destination or without, if you're interested only in finding a Hamiltonian path. But if you want to have a circuit, then of course it doesn't really matter where you start and where you start, but where you finish. Well, start and finish would be the same in a circuit. And of course, in a circuit, it doesn't really matter where you start and where you finish, because you have to visit every vertex once anyway. So if you have a circuit starting in A, then of course you also have a circuit starting in B and C and so on. All right, so this has a Hamiltonian path, takes as argument source and destination. We say that at the beginning we haven't visited any vertex, and then we call a depth-first search for a Hamiltonian cycle, or a general path from source to destination, with the number of vertices minus 1. This is how deep we have to go in order to be sure that we have found, that we have visited all the vertices. Now, the Hamiltonian recursive algorithm takes as input a graph, the vertex where we currently are, the destination vertex where we want to finally end. If we're looking for a circuit, this would be the source node that we want to start with. And D is the distance remaining until a path is found. At the beginning, the distance is maximal. We want to visit all the vertices. And as we go deeper into the search, we will reduce the depth that we are looking for as we have found and visited vertices on our path. So if we have reached the destination node and the distance that remains is 0, then we can return true. But we can return true only if the distance remains 0. If we have reached the destination, but the distance is greater than 0, we have to return false. And that's because if the distance is greater than 0, we haven't visited all the vertices. We aren't deep enough in our search. And we have to find another way to get to our destination. Else, if that is not the case, then we set visited v to true. And then we look at all the neighbors that have not been visited. And here you see I'm using some logical symbols just to make that shorter. You hopefully all know that this stands for conjunction and this symbol stands for not. So what I'm saying is that I'm looking for edges so that W, the neighboring node, has not been visited yet. And I continue my depth first search with that new vertex W and with a reduced depth, because I've visited one more vertex. And if the depth before that was 10, then the depth now would be 9, and so on. If the recursive call is successful, then eventually I must have reached this case here, that the distance was 0. And I have reached the destination. So if one of the recursive calls gives us a successful solution, then we know we have found a successful solution. If, on the other hand, we have exhausted all of this, then we have to backtrack. We have to say, well, visiting V next doesn't really work. We can't find a Hamiltonian path from here. So we unset that marker that we have visited this vertex, because we might have to come back to V via a different route in order to finally get to a Hamiltonian path. That's the algorithm. Now let's, before the break, have a look at this example here and see if we can find a Hamiltonian path from 1. So now I want to start at 1 to 6. First question, is there a Hamiltonian path? Will we be able to find one? Can you go from 1 to 6? Yes? Okay, how? Yes, so so it sounds like most of you found it, 1, 0, 2, 3. We can't go to 5. We have to go back later. 4, 8, 9, 7, 5, and 6. There is probably more. You can go from 3 to, did we go through 8, 9, 7, 4, 5, 6? So there's several ways you can transcend this graph here. We will see that with the help of our depth first search, if we consider neighbors in ascending order, we will systematically generate exactly one such path. Okay, let's see what happens when we apply our depth first search here, this Hamiltonian path. We have to visit all the nodes, and it was said that we want to start at vertex number 1. So when we do standard depth first search at node 1, what would happen first? We would go to, if we visit neighbors in ascending order, the next one would be 0. Then 2, yes. Yep. Yes. Correct. 6. So now we've reached the destination. We wanted to go from 1 to 6, but what is the problem? If we count the length and we consider our counter, then the distance that we started with, the number of vertices minus 1, is not, how many have we got? We have 10 vertices should be 9, but the distance is not 0 because we haven't visited enough vertices. And you see that the distance is always reduced. We start with 9 every time we go into that search. But if you have 8, 7, 6, 5, 4, 3, we have missed 3 vertices. And indeed, we haven't visited 7, 8, and 9. So it is indeed the case that we've reached the destination, but we haven't visited all the vertices. And this is why this if then else in the algorithm returns false. And that means that we have to go back to the latest choice point in that recursive call, which would have been where? At 5? Yes. So instead of going to 6, we would have gone to any other choice that we have here? 7. Yeah. So we can't go 3, 4 because we've already been there. We can go to 7. Yeah. Yes. And that's it. There's no unvisited neighbor anymore, and we have reached the destination. And also, if you look at the count, we have now missed node 6. Even if we didn't care about the destination, we wouldn't have reached depth 0. So we have to backtrack from there as well. What other choice would I have had? Any other choice from 8? No. 7? Yes, that's exactly right. 7. I could have gone to 9 and then to 8. Not that that helps at all, because now I'm stuck at 8 and I can't go anywhere else from here. So that choice from 7 didn't get us anywhere. So let's go back to 5. Is there any other possibility to continue from 5 instead of 7? No, we've looked at 4 and 3 previously. We have checked 6 and came back from that recursive call. So instead of going to 5 from 4, we would consider other possibilities from 4. So just to make clear where we are here. Can we still see it? Yep. So 4, we would go to 7. Is it really 8? 5. We have unmarked 5 because we went beyond 5 back to 4. So we can go 4, 7, 5, and then 6. 7, 5, 6. This is what we would consider next. But again, the depth is not 0. This path is not long enough because it's missing 2 nodes. It's a bit better than the one that we found here when we reached 6, but it's still missing 2 nodes. So that doesn't work either. From 4 to 7. Now we can try 8. That gives me 4, 8, 7, 5, 6, but I'm still missing 9. Then that was 4, 7. Now let's go from 4 to 8. So I'm not writing this down, but I'm writing down 4 to 8. And 5, 6, still not 9. So 4, 8, 9. And 5 and 6. And that's it. So now we have visited all the nodes, and you can see that our count would have counted down from 10 if we take this path down to 0. And this would be the one that our depth-first search returns as the first Hamiltonian path that is found from 0 to 6 in this graph. Again, it's very nice that we can use this standard depth-first search technique. We just have to fiddle around a little with some of the parameters, introduce this counter, but basically it's a standard depth-first search that we can apply here just as well. All right, really time for a break. Let me just... This is the answer. We have looked at all these possibilities, and we have seen that in some cases we haven't reached 0, and in other cases we have had no unvisited neighbor. A nice little exercise for you might be to try that with the source node 0 and the destination, and see if you can find a Hamiltonian path there. You can look at the graph and see if you can find one, and if you can't find one, you can try the algorithm and see if it does find one. Last comment, why is that so complex and why is that so difficult? The problem is, in the worst case, you have to consider all possible paths, and there are factorial v minus 1 paths to be examined. The problem is if you have a graph with an isolated vertex and the rest is fully connected, and you want to see whether there is a Hamiltonian path from x to 0, then obviously you can't do that, but you have to consider, by this algorithm, all the possible ways depth-first search can work here from any x. And only once you've exhausted all these possible combinations, which is characterized by that factorial, then you can be sure that there is no possible path to 0. So starting from any x, there are 3 factorial paths. So in total, you have to check 4 factorial total paths, which is 4 times 3 times 2. And of course, there's no path of length 5. Whatever you do, you can never reach 0. Now, as I said earlier, there's no known simpler algorithm. In the worst case, you really have to check all possible paths until someone finds a polynomial algorithm. Of course, if we had applied our connected component array, then we could have first of all checked whether it is even possible to go from one node to another node. And if we have more than one connected component, then it's clear that we can't have a Hamiltonian path. But this is only a very special case, and in general, there's no simple solution to decide that a Hamiltonian path doesn't exist. And with this, before we move to Euler graphs, Euler circuits, which is the dual problem to this, let me have a break of about 10 minutes and start at 7:25 again. All right. Let's continue. Now, one of you pointed out that during the when I ran the breadth-first search through that example, that actually the visited array that I ended up with was different from this one, and actually had a 5 in here, I think, instead of a 4. If you have followed what I did, please make sure that you correct this. And I know that what is written here, I think would be correct, but to make sure that it is, I spent the break quickly looking at the program that I've provided on our webpage, breadth-first search queue, which just implements the breadth-first search with the queue. As you can see here, it creates a new queue, adds the source node to it, and then runs while the queue is not empty. If you have found the destination, you return true. And other than that, you put every new node on the queue that hasn't been visited before, and you record where it came from. So that's the standard implementation that is available that you can run. And I have built exactly the same graph as on the slide here, just to demonstrate how that works. And if it finds a path from source to destination, which it tries to find here from 0 to 6, which was the example that we looked at, then it prints the path in reversed order. And now to ensure that this array, or to check whether what I showed you here is actually correct, I've added this loop that prints out that array, and we can just check whether what I did during class is correct or what I have here on the slide is correct. Now, what you see here is you can compile the breadth-first search queue, which uses a standard queue implementation that is available and a graph implementation, and creates a program called BFS, which uses exactly the same graph. And if I run it now, then first of all, it outputs the graph that we were expecting, the shortest graph, read backwards from 0 to 5 to 6. And now it also outputs the visited array, and we can see 0, 0, 0, 2, 5, 0, 5, 4. So there should really be a 4. What I had here on the slide is correct. This is what happens in the algorithm. And -1 is the only node that we haven't ever put on the queue. Number 9 still remains at -1, as you can see here from the program. Okay, I can also show you, while I'm at it, this is the queue that we have used, but we don't have to look at this. We can look at this program, which is the implementation of the Hamiltonian search algorithm using the recursive depth-first search. It implements just the algorithm, but it implements exactly the algorithm that we have seen. If the remaining depth is 0, then we can return true once we found the destination. If it's not 0, this algorithm would return false. And other than that, it would just apply the Hamiltonian algorithm in exactly the same way that we have seen now implemented as C and as a C program. And most importantly, when we went through that loop and we couldn't find a Hamiltonian path, we have to reset the flag that V has been visited, because we might have to find another way to get to V. And this has Hamiltonian path is exactly what we have seen as an algorithm. And this program here now allows you to input an arbitrary graph, and it also asks you to enter from and, well, it asks you to, where is that? Up here. So it does ask you for all the edges, but before that it asks you for the source and destination for the Hamiltonian path. And then it outputs whether or not the graph has a Hamiltonian path. There's one particular example that I've put here. The test graph H, which is exactly the graph that we looked at. It has 10 nodes, and these are, I want to find a Hamiltonian path from 1 to 6. This is what we have done, and these are all the edges that are read as user input. We can see what our algorithm says. Hamiltonian, caps lock, it's not a good idea. So it compiles Hamiltonian, it uses our standard graph abstract data type. And then I can run this program. But this would now require to enter a graph all by myself. Well, we can use a very simple graph with 2 vertices. We want to go from 0 to 1, and we have an edge from 0 to 1. Then the answer should, of course, be yes. That's it. We only want to have that one edge. Yes, it says there is a Hamiltonian path from 0 to 1. That's not particularly interesting. Let me take the test graph H. And, well, it reads all the edges. This is the output. And in the end, it says there is a Hamiltonian path, which would be exactly the one that we have found. Okay. All right. So that was the breadth-first search. Let me go back to where we were. Hamiltonian paths, I think 23. Yes, we looked at this slide. Now let's look at the dual problem to check whether a graph has what is known as an Euler path. This would be a path connecting 2 vertices in a graph so that the path includes every edge exactly once. The path doesn't have to be simple. Unlike a Hamiltonian path, you can visit vertices more than once. And just like with Hamiltonian paths, we make the distinction that if we go back to the vertex we came from, then we call this an Euler circuit. If we look at this graph here, you want to visit every edge exactly once. Then this is possible. For instance, if you start at 4, 3, 1, well, you can go 5, 2, or you can go 1, 2, 5. This visits every edge once. You can also start at 1, 5, 2, back to 1, 3, 4. But what you can't do is start at 3, for example. Because then you can visit all these edges here, but you would have to visit this edge twice, and you're not allowed to do that. This obviously has an Euler circuit. This is very clear. What are real-world applications of trying to find an Euler path? If you want to visit all edges of a graph, Postman, garbage pickup, that would be typical examples. Now, this problem is named after a Swiss mathematician, physicist, astronomer, logician, and engineer. Anything you can imagine. Leonhard Euler, and because he was Swiss, he is pronounced not like you would pronounce Europe, Euler. He really is pronounced Euler. What can we say about trying to find out whether a graph admits an Euler path or an Euler circuit? Now there is a simple possible brute force approach. You, just like with the Hamiltonian paths, you look at all possible paths and check whether they satisfy the requirement that every edge has been visited. And you can do that in the same way. You just count the number of, or you know the number of edges, and then you use a counter that counts down, and only if you have found a path that visited every edge exactly once, then you would say, yes, there is one. Now, unlike Hamiltonian paths, there's actually a much simpler algorithm that, because if you do it in this way, it would result in a factorial time performance just like the Hamiltonian path problem. But you can apply a simpler algorithm based on 2 theorems. First one says that a graph has an Euler circuit. if and only if the graph is connected. That is, you don't have two disconnected components, in which case this would not be possible. And all vertices have even degree. That's a very simple criterion that you can check. Remember that degree is the number of edges incident to a vertex. That is, you just count the number of edges from / to a vertex, and it has to be even. And that has to be true for all the vertices that the graph contains. Now, intuitively, this is the case because if you want to find an Euler circuit, every time you get into a vertex, you also have to get out of a vertex, and you have to use a different edge to do this. So every time you get in with one edge, you have to find another edge to get out. You might get back in with a third edge, but then you have to find a fourth edge to get out again. And that means that you have to have an even number of edges. You can possibly do that with an odd number of edges. We can see that with this example here, all 5 vertices, they have even degree. The degree is 2 because there's exactly 2 edges for every vertex. Now, this is not the case here. Here you have one node with odd degree, only one, and you have another one with odd degree. But all the others, they have even degree. And remember what I just said applies only to circuits. When we are not looking for a circuit, but for a path, then the theorem says that a graph has a non-circuitous Euler path if and only if, again, it is connected. And there are exactly 2 vertices that have odd degree. Now, why is that the case? If you don't want to go back, then from the starting node, you have to get out. But you don't want to come back, so you don't have to get in. Well, maybe you do get in, but then you want to get out again. So that starting vertex should actually have odd degree. You once want to get out, and then every time you get in, you want to get out. And the same is true for the destination. You only want to get in, and every time you get out, you want to come back in. So that also needs odd degree. And this explains why we have to have exactly 2 vertices of odd degree. Plus, when you then look at a graph like this, and you're asked to find an Euler path, then you can count the degrees, and you can see 1 and 4 have odd degree. So every Euler path has to start in 1 and end in 4, or has to start in 4 and end in 1. And you can verify that you can't start in 2, you can't start in 5, and you cannot start in 3. This is not possible. So this is a very, very nice criterion, which can be used to decide whether a graph has an Euler path or a circuit without doing a complicated search. So quickly check whether you can apply this criterion. The first graph, does it have an Euler path? Does it have an Euler circuit? No, the first graph has neither. We have degree 3 here, we have degree 3 here, and we have degree 3 here. And we have degree 5. So there are lots of nodes with odd degree, and that means we don't have a circuit and we don't have an Euler path. Do we have a Hamiltonian path? Yeah, there are enough edges, so that is very easy. But now we are interested in Euler paths and Euler circuits. What about this one? Yes, it does not have an Euler circuit, because here we have an odd degree with 5, and node 2 has odd degree. So every path has to start in 2 and end in 5, or the other way around. And then it's quite easy. We can go from 5 to 4 and just in that direction, or from 5 to 2 and then in this direction and visit all the edges exactly once. So that's a very nice criterion, which we have applied here. And we can easily find an Euler path, which leads to a nice algorithm where we can just check, use that these two theorems, whether a graph does have an Euler path or an Euler circuit without doing a complicated search. What it does require is the existence of a function that determines the degree of a vertex in a graph. If you have done your homework diligently, you would have implemented a program last week which was asking you to compute the degree of every vertex in a graph. And it's quite easy. You just have to cycle through all the other vertices, check whether they are adjacent to a current vertex, and if they are, then increment a counter that counts the number of edges incident to a vertex. So that degree function is being used in this algorithm, and this algorithm checks whether there is an Euler path. It can also be used to check an Euler circuit because it takes source and destination, two vertices, as argument. If source and destination are identical, then we are obviously asking for an Euler circuit. So what does that algorithm do? It's really very simple. It applies that criterion from the theorem. It says that if the source is not the same as the destination, which means we're not looking for a circuit, we are looking for a path, then we know that we have to start in a node with odd degree, and we have to end in a node of odd degree. So if the degree of the source node is actually even, or the degree of this destination node is even, then we can't have a path from source to destination. When we consider the case where source and destination are actually the same, then all the nodes have to be of even degree. So if the degree of the source is odd, then for a path that would have been good, but for a circuit, this means we don't have a circuit, and therefore it returns false. The last check that it does is for all other vertices that are not the source and the destination, we have to make sure that they are all of even degree. So as soon as we have one vertex whose degree is odd, the answer is no. And you can go back to the web page, and you will see a C program that implements this algorithm with the help of a function that calculates the degree of a vertex and then determines whether a given graph does have an Euler circuit or an Euler path from a specific source to a specific destination. And you will see likewise a test graph that I have given as input, and then you can play around with that program as well. If we look at the complexity of this algorithm, then under the assumption that we've already checked connectivity, so we would only run this algorithm if we know that the graph is connected, we assume that we have computed the degree for every vertex. So this is really just a lookup table. Then the algorithm itself was a single loop over all vertices. We basically had to check whether all vertices have degree even. And therefore, the time complexity for this algorithm would simply be OV for that single loop. On the other hand, if we haven't computed the degree, and we actually have to do it, then the cost to compute the degree of a single vertex would be OV. And if you have to then do that for all the vertices, the overall cost is OV square. But still, that means the problem is tractable, deciding whether a graph has an Euler circuit or an Euler path. Tractable in the sense that we have a polynomial algorithm, not only just exponential algorithms. Now, this just determines whether a graph has an Euler path or an Euler circuit. If you're interested in looking at an algorithm that is actually linear time in the number of edges that computes an Euler path, then I refer to that Sedgwick textbook, chapter 17.7, where he explains in detail an algorithm that does find such an Euler path. This is going beyond the contents of this course, which is why I'm only referring to it. But as I said, if you're interested in, you can have a look. What I will now do for the rest of this chapter is I will be looking at an extension of the types of graphs that we have looked at so far, where we didn't distinguish the direction of graphs, of edges. Now we will be looking at so-called directed graphs. Previously, an edge from V to W was the same as from W to V, but if we have directed graphs, then that might be different. Previously, undirected graphs means there is a relationship between two vertices, but nothing else. Whereas, and in particular, this relationship was symmetric. They are related or not. In many real-world applications, however, edges are directional. Think Google Maps where you have a one-way street, then this is directional. And there are many other examples of graphs that are directional. What was other examples? Twitter, if your X follows Y, then not necessarily Y follows X. And if you look at links on web pages, if web page X has a link to web page Y, then that of course doesn't mean that there's also a link from web page Y to web page X. So that's one thing that we will consider today, and next week we will be looking at edges that also have weights, cost to go from V to W. Now we've already seen that if we have a directed graph, or as they are also known, a digraph, then we can represent this with, for example, an adjacency matrix, where in case of undirectional or undirected graphs, we have a symmetric matrix, which actually allows us to use a more efficient representation where we only encode 1/2 of the matrix. But we can't do that anymore if we have directed graphs. That is, all our edges are directed. Then this matrix is no longer symmetric. So here we have an example of a digraph, a directed graph, where you can see that sometimes we have edges from a node to another node, and also the edge from that node back to this node. But not necessarily. So you can go from B to C and C to B, and therefore we have a 1 here, B to C, and also a 1 C to B. But you can't, for instance, go from D, you can go from D to B, but not back. So we have a 1 here, but a 0 here. We will also consider for digraphs that you can have loops, and therefore you can have a 1 somewhere in this diagonal. For instance, there is a self-loop A to A and another self-loop G to G that you can see here. The maximum number of edges in a digraph with V vertices is now twice the number that we had before, plus the fact that we consider loops. So now we can really have as many edges as we have cells in this matrix. So it's no longer V times V minus 1 divided by 2, but here we consider that the maximum number of edges is V square. When we talk about digraphs, then we sometimes talk about directed paths. Although when you have a digraph and someone says path, then they always mean that there is a directed path. So you can use edges only in the direction in which they have been defined. So a directed path in a digraph would be a sequence of at least 2 vertices, V1, V2, and so on to Vn, where you have a directed edge from Vi to its successor Vi plus 1 for all those in the sequence. So you only use edges in the direction in which they have been defined. If V1 is the same as Vn, then as before we have a cycle, and we call this now a directed cycle. Now here you could have a very simple directed cycle from B to C and from C to B. But the cycle from B to C could also use B, C, D, and B. But you can't go, what is this? This clockwise. You can't go anti-clockwise because that would violate the direction of these 2 edges. What's a more interesting problem for directed graphs is reachability. We say that a node W is reachable from a node V if there is a directed path from V to W. Now, for undirected graphs, it was very easy to test reachability once we've computed connected components. We knew that two vertices in the same component are always reachable because we looked at undirected graphs. But here, with the directed vertices, it might not be that straightforward and easy to see whether there is a particular node W reachable from another node V. Now, here are even more examples, apart from those that I've already mentioned. Web pages and hyperlinks, they are obviously directed, as I said. Not every link will find its counterpart on the other web page. You could look at scheduling as a domain where every task that you have is a vertex, and you use an arrow to indicate precedence. So you say one task must be performed before the other task, and then typically you don't have another edge in the other direction. That wouldn't work. Other applications are games where you have board positions, and then you say a legal move takes one board position to the next board position, and that does not necessarily mean in a game that you have a reverse move that takes you from the resulting position back to the previous position. And there are lots of other examples. Make might be interesting. A vertex is every file, and you can define the dependency. One file depends on another, and this typically is directed also. What are interesting problems to solve on digraphs? We might be interested in, say, finding out if there is a directed path, reachability, transitive closure, and this is the last problem that we will be looking at today. Shortest path from S to T. We won't be looking at this directed path then, obviously. We won't be looking at this today, but next week when we also introduce weights. Strong connectivity. Are all vertices mutually reachable? Topological sort might be if you have this task network and one has to precede another, is it possible to arrange all the tasks in such a way that all the precedence relations are satisfied? A very interesting application for directed graphs, which Google does, and where they haven't really published the algorithm that they are using, is to determine how important web pages are. Google ranks all the search results according to importance, and Google is so particularly popular because you typically get the result that you're looking for as one of the first results. And that's got to do with them ranking all the web pages with the help of a page rank algorithm. Everyone knows roughly how it works, but the precise algorithm is unknown. You might also be interested in building a web crawler that Google also uses that traverses the entire World Wide Web in order to visit every possible linked web page. And this is the only way in which they can deliver search results. Now, with regard to representation, we have a similar set of choices as for undirected or undirectional graphs. We can use an array of edges, but now they must be directed. We can use a vertex indexed adjacency matrix. If you look at this digraph, then that is the adjacency matrix that corresponds to all the directed edges. Or you can use an adjacency list like we have used before, where you have all the adjacent vertices here. And again, it's not symmetric. Just because a node appears in the adjacency list of one node doesn't mean that this one node appears in the adjacency list of the other node. This is the case with 0 and 1, but not with 0 and 3, for example. Now, the one problem that I want to consider on directed graphs is the question about reachability. Which nodes are reachable from other nodes via a directed path? This is very useful to know. Given the directed graph, is a given vertex T reachable from vertex S? And coming back to the scheduling problem, can I complete a schedule if I'm in a current state? Is it possible to reach via that precedence relation another state? Or is a malloc object being referenced by any pointer? That might also be interesting if you have a graph that represents the dependencies, then you can find if you have or haven't lost any memory that has been allocated and that you can't deallocate anymore because you've lost that reference. Now the question is, how can we compute transitive closure? The algorithm that you could use is you could take a has path function that in itself is implemented by a depth first or a breadth first search algorithm. You can apply DFS and BFS in exactly the same way we have applied it for undirected graphs. The only difference is you would obviously only choose a neighbor W if it is reachable via a directed graph from V and not the other way around. Now this would work if you're interested in checking whether S and T are reachable only very infrequently. But if you have an algorithm that all the time has to check whether some S and some T are, or whether some T is reachable from S or not, then it might be a good idea to calculate that reachability once and for all for a given graph, and then use that array just to check. In this case, the reachable would just be, let's say we have an array that I call TC because this is known as the transitive closure. I would just return whether or not S and T are connected in that after I've computed the transitive closure in that array. Now this is very convenient to have, and we will see there is a relatively efficient algorithm to do this. Of course, if V is very, very large, then this is not feasible because it does require that two-dimensional array for the transitive closure. And it's not, for example, possible for Google to keep a matrix of all possible web pages and see whether you can, via a sequence of links, reach one web page through another. And that's only because you have way too many web pages for you to maintain this squared array. But if you have a reasonably small graph, then it can be a good thing to pre-compute the reachability, the transitive closure matrix. Let's go back to this graph here. What do you think if you look at this graph? Is every node reachable from every other node? Or do you see cases where one node is not reachable? E is not reachable. That's right. E is not reachable by any other or from any other vertex. What about other vertices? Is there other cases where one vertex is not reachable by the other, from the other? G cannot reach other node. So if you are in G, then you can go to G, but you can't go anywhere else. Other than that, there are enough edges to go around. You can go DFA. Someone said C, but no, you can go via B, and there are circles here, etc. Now this is a bit more difficult to see, as you can see, whereas if these were undirected edges, we would immediately say that this graph is connected. So let's see what we have here. This is indeed the reachability matrix. You can see from G, you can reach G, but no other node. And E cannot be reached from any of the nodes in the graph. So when you then want to check reachability between two different nodes, if you've computed that transitive closure, that reachability matrix, the answer is very easy to give. Whereas when you look at this matrix, it is certainly much harder to decide whether you can go from A to F. Whereas the answer is obviously yes when you look at that transitive closure. So that's the last algorithm that we will be looking at for today. we will be looking at a very nice, actually, algorithm that allows us to produce a matrix of reachability values so that that matrix TC, transitive closure, contains or is 1 if T is reachable from S and 0 if T is not reachable from S. Now, the algorithm that I'm going to show you is based on the following observation. It says that for all vertices I and S and T, you want to go from S to T, you have that if I can be reached from S via a directed edge, and if you can go from I to T via a directed edge, then the transitive closure matrix ST must have a 1. Why is that so? It says that if you have a path from S to T of length 2, which goes via a vertex I, then of course T is reachable from S with the help of a path of length 2. Now, this is obviously true for all vertices I and for all vertices S and all vertices T. And that leads to an algorithm that applies this concept of going not directly from S to T, but going from S via I to another vertex T. And if you calculate that systematically, then you will see that having this one condition, that instead of going directly from S to T, you just have to find a third vertex I, so that you go from S to I and then from I to T, that suffices to calculate all entries in the transitive closure matrix. This is what this algorithm does. It's extremely simple if you look at it. And it only uses 3 nested loops instead of, let's say, if you have V vertices, that you need V nested loops to do that calculation. What does it do? It says that go through all vertices G, and then into inner loops, check whether, when you have an arbitrary vertex S and an arbitrary vertex T, so that you already know that you're going to go from S to I, which you have in your outer loop, and from I to T, then you know that you can also go from S to T. Now, it is very clear that this is correct what you're doing here. If you can go from S to I and you can go from I to T, then you can also go from S to T. What's really interesting is that this suffices to compute the entire transitive closure. So you only need to look for these paths of length 2 from S to T to be able to compute every reachability question. And even though this algorithm is so simple, because it's not entirely clear that and why it really works, it is known by its inventor, or the first one who not only wrote that algorithm but also proved that this allows you to compute the transitive closure for arbitrary matrices, Warshall, and this is why this is known as Warshall's algorithm. Now, I believe this is the first algorithm that has the name, or has been given a name, unlike the problems that we looked at, an actual algorithm that has been named after the person who has first published this algorithm. We will see that happening a lot as we go to more interesting and more complicated algorithms. Many of them are known by their inventors. Now, why and how does that algorithm work? The reason why it works is that after the first iteration, well, first of all, you initialize the transitive closure with the edges that you have. If you have an edge from S to D, then of course this should be in the transitive closure. But now you can extend this by saying that after iteration 1, this transitive closure array would have a 1 if either this is a direct edge and it was initialized as you can go from S to T, or there exists a path of length 2 via that node 0. You can go from S to 0 with a direct edge, and from 0 to T with a direct edge. And why is that so? Well, we start with the first vertex. If we do that systematically, we would start with 0, and we would be looking for all paths of length 2 that go through 0. Now, the interesting thing is, as you go through that outer loop, you will see that you cater for larger and larger, longer and longer paths. That is, given that after iteration 1, you have a direct connection from S to 2 in the transitive closure matrix, if there exists that path of length 2. So you know that after iteration 2, where you now take into account vertex 1, you have a 1 in the transitive closure matrix, if any of the following cases is true. Either you have a direct edge, then it was initialized as such, or you have a path from S to T via 0. Why is that true? Because that was already in here. Or you have that direct path from S to D of length 2 via 1, because this is what we do in that second iteration. But most importantly, you would also get a 1 here if you have a path from S via 0 via 1 to T. So that's now a path of length 3. Why do you get that as well? You get that because you do know that you can go from S to 1 in the transitive closure matrix after the first iteration. So TCS1 would also be true, simply because it would have been set true in that first iteration. So you would know that you can go from S to 1 in one step, and you can go, obviously, in one step with that direct edge from 1 to T. So in that second iteration, you would now take into account all paths of length 2 that use nodes 0 and 1. And of course, this would happen the other way around as well. So actually, you will see that after the vth iteration, if you went through all possible paths, all vertices, first you start with 0, then you consider 1, and then you go to 2, 3, 4, and so on, to V. That after the vth iteration, you have set the transitive closure matrix to 1 if there is any directed path from S to T via any of these other nodes. And this is why this algorithm is so beautiful. It just uses these 3 nested loops, and it allows you to compute paths of arbitrary length. Now let's see with this example how we compute the transitive closure with the help of that simple algorithm. All right, so that's our directed graph. This is the matrix that we want to start with. This just contains the arrows that we have in here. Now, the question is, what happens when we apply the algorithm with the first iteration of the outermost loop? We start with vertex 0. And the question is, of course, we have the direct paths from 0 to somewhere and from somewhere to 0. But can we also go via 0 from one vertex to another one? This is what the 2 inner loops would do. They would check all pairs of vertices S and T that can go, so that you can go from S to T via 0. Can you see any of these zeros that change to 1? Can you take 0 as an intermediate node for a path of length 2? One, 2, 3, yes. So you don't have an edge from 1 to 3, but you can go from 1 to 0 and from 0 to 3. So if you look at 1 and 3, they would satisfy the fact that you can go from 1 to 0, the I, which is our outer index, and from 0 to 3. So indeed, 1 to 3 that changes to 1. Can we see that? Yeah, that works. Any other example? 1 to 2. Yes, but this we already have. So indeed, you can go via 0 to 2, but this wouldn't change the matrix because we already have this. Very good. Yes, you can go from 1, did you say 1? To it, 1 to itself. Yes, you can go from 1 to 0 and back to 1. So if S and T in that inner loops are both 1, then you would set this to 1 as well. And that really is everything that changes via node 0. Next iteration via node 1. Now, given all these 1s that we have inserted here, can you find more examples of paths that use 1 as an intermediate node? 2 to 0. Yes, that changes to 1 because 2, 1, 0. Yep. 2 to itself. Very good. 2 to itself. Well, first up, then down. And 0 to itself. That's right. 0 to 1, 1 to 0. That changes. Anything else? Ah, 2 to 3. And why do we have to change 2 to 3? Because you can go via 1, and we know that we can go from 1 to 3. And we have computed that because previously we see now we can go from 1 to 3. So now we can go from 2 via 1 also to 3. So that changes as well. And this is the beauty of this algorithm, that it also does this check here, or adds this 1, because we have computed in a sense, the direct edge from 1 to 3 in the previous iteration. So somehow this was added in the iteration before, and therefore we can see now we can go via 1 also to 3. This is really how the algorithm works. Is there anything that we can do with 2? Anything else that we can do? Not really. 2 doesn't help us to go anywhere where we haven't been before. And with 3, no, we can't go from 3 anywhere. So considering 3 in the last loop doesn't take us any further as well. So that this is the reachability matrix that we have computed here. And you can see that every node is reachable from every other node, except that we can't reach anything from 3. So that's what Warshall's algorithm does. We have seen that the algorithm terminates at the end, but we can see that after the second iteration, we have already reached the transitive closure because nothing else changes anymore. But of course, the algorithm has to run until the end because you don't know whether this really is the transitive closure or not. To determine when the algorithm would have reached the transitive closure, you could, for example, look at the graph, and you can check whether there are any paths that use more than these nodes 0 and 1 that are in the transitive closure but don't go via 0 and 1. And you see there's no other path in this case, and therefore, by inspecting the graph, you would know that just by considering 0 and then considering 1, you have already reached the transitive closure. Now, the cost analysis is really very straightforward. The storage is obviously V² items. You can use a compact representation where every item is just 1 bit, reachable or not reachable. And the computation of the transitive closure, just by inspecting the algorithm with the 3 nested loops that all run through all the vertices. Obviously, the complexity is V³ v to the power of 3. And once you've computed the reachability array or the transitive closure, computation of reachable itself is just a lookup in the matrix. Now that would be useful if you have many calls to reachable. If you have an algorithm or a problem where you have to compute reachable for 2 vertices and only very few, then it's not worth doing that v cube computation. But if you have lots of calls to reachable, then it makes sense to compute that transitive closure first. The alternative would be that you use depth first search every time you call reachable. The storage would be the cost of, if we use depth first search, I should have said stack instead of queue. You could also use breadth first search with a queue. And the computation cost would be the cost of depth first search, which we have seen would be v square if we use an adjacency matrix. And of course, we know it's v plus e if we use an adjacency list. Right. I believe that this was the last algorithm that I wanted to introduce you to. Now, just in the interest of time, to make sure that I've got enough time to show you the mock quiz on Moodle and that we can have the fun quiz, what I have for the last few remaining slides in this chapter on algorithms is more looking at problems that Google has, for example, PageRank. This is not going to be relevant for the mid-session tests next week, and this is why I'm going to skip that and leave that until next week, so that we stop here all the way up to the transitive closure. That can be part of the midterm test, and I will now have another break for, let's say, until 8:25, and then I will quickly show you how to access and do the mock quiz on Moodle, and then we will have our fun quiz. All right, so guys, now listen, everyone. So this is kind of important for you next week. So what you will have to do, everyone, in order to access the midterm online test, you have to log into Moodle for our course. And you can do that, for example, via lecture recordings, but I will also send around a notice with the link. So you do click on that Moodle for this particular course. You have to log in with your ZID, as you probably know. And then what you will see at the moment is something like this. There isn't really anything on that web page because we are only using this for the recordings, which if you have listened to it, you can access through that lecture videos. But there's now one section called online test. And there's one test, this mock test. And then later this week, we will add the mid-session test, either above or below. If you can't see it, then maybe you land here, then just click at open this, and then you will see these tests. Now, this one says 1 hour time limit, opens 4 September, which is today at 4. This is when it was opened. And it actually closes on Sunday at 12 noon. So you've got time yourself to click on it and then answer these questions yourself, submit, and then wait until 12 noon to get your feedback. Now, this is a mock test, so you can answer whatever you like, and it obviously doesn't count, just for you to get used to it, but also to give you examples of questions that might resemble those that you will then actually get. But I do click on it and just show you what happens when you click on it. First of all, you see all that information again. It has already opened. It will close on Sunday. And it reminds you there is a time limit of 1 hour. Now, when you click on Attempt Quiz Now, it makes sure that you only start the attempt, knowing that you have then, once you click on Start the Attempt, exactly 1 hour to finish that quiz. So make sure that you're prepared. Make sure that you have a stable internet connection. It might be a good idea to do it on Monday afternoon while you're here at the university. If a computer breaks down, then you can easily go to another computer. And what does happen is, if you happen to be logged out automatically because of any problem, you can log in and you can continue the quiz at the point where you left it. So all the answers that you have already put in, they will automatically be saved. The clock, however, is ticking. You can't just log out and then wait for an hour. That would mean that then the hour is over. So as soon as you really start the attempt, what happens is that there is a clock somewhere which would be ticking down. It's down here. Actually, on my browser, the Google Chrome I think I used, it was a bit nicer because this quiz navigation was actually to the left of the questions. Let me see if yeah, so this is better. Use full screen, it does work better. So what you can see here, there are 3 questions, and in the real test you will see 10 questions here. You see the timer, and now I'm showing you just 3 types of questions that you might encounter. There might be questions like this: tick all correct ways, and then there's a question. You see some program code. It's a multiple choice question, and it is one when it says select one or more, where quite possibly there's more than one correct answer. And you have to give all answers to get the maximum score for that question. What you can see here is what this question is worth, 2 marks. The way I have set it up for the mid-session test is that the first 5 questions are the simpler questions. They are all worth 1 mark. And the second 5 questions, they are worth 2 marks. But you can always see that with every question here. Now, I'm not looking at this here. I'm just randomly ticking this. What I want to illustrate is that suppose there are 2 correct answers and 2 wrong answers. Suppose the first 2 are correct. Then by ticking 1 correct answer, you will get 50%. That is 1 mark. by ticking this, you will get another 50%. That would give you 100% or exactly 2 marks. But by ticking a wrong answer, you're actually going backwards. Every wrong answer, if there's 2 wrong answers, means that 50% are deducted. So you can be sure that you get all correct answers by clicking all of them. But by that calculation, that obviously only works if really all 4 questions or 4 answers are correct. Any questions on that? Okay, now let me just leave those 2. You can then move to the next question either by next page, or you can always click on these here to move between these questions. So that was your question at the beginning. You can freely jump between these questions, and you even see which questions you have already answered. Now here you have a graph question with a graph embedded. And this is not a multiple choice question. It actually asks you to input a number. Here the question is, well, you can read it yourself, and maybe you don't want to read it because you want to do the test as if it was the real test. But that requires you to input a number. This one is very likely not correct. But it is one that you can input. And you see that with that navigation here, you have given answers here. What you can also do is you may flag this question to indicate that you're not sure whether this answer is correct. And then you can see that there's this one where you probably would want to go back. And then you have questions that require you not to input a number, but real actual text. And it is very, very important that you follow the instruction on how to input that. It's made very, very clear how you do it, but make sure that you read it carefully. If you are asked to enter a path in this following format, dash separated, no spaces, then please do enter that path in that format. So if your path is 875, then you want to input it in this way and not 875. Just follow the instruction and then give this answer. Now, once you're satisfied with your answers, here you would still have 55 minutes to answer these questions. You can either click on Finish Attempt here. You can click on Next Page, and at the very end, you can click on Finish Attempt. That doesn't really submit the answers yet. You can still return to the attempt. A clock is, of course, ticking. Finish Attempt. Submit all and finish is what you then want to do. Here it actually tells you that I started at 8:28, at 9:28 I have to finish. And even then you're warned that this is that your final answer, submit all and finish. And once you press submit all and finish, it will have submitted. The system is smart enough that if you don't submit on time, it will actually submit automatically. I've set it up in such a way that you don't even have to do that. If you're satisfied with your answers, you can leave it and just let the clock time out, and it will be automatically submitted. But it might just be safer if you're really happy with your answers to click Submit All and Finish. Are there any questions before I do that with this test? Because then I can't go back anymore. And you cannot do it multiple times. The mock test, no, you can't do it multiple times. The reason is that I've set it up exactly the same way as the actual test. So what happens if I submit all, or you submit all and finish, is that these answers will be stored. And at the end of this test, which will be Sunday noon, you will get feedback. And that illustrates and shows you how you will get feedback for the actual mid-session test.
Will our questions be the same as the ones we just saw there?
Sorry? For the mock test, yes, but not for the mid-session test. Yep.
What if there's only one correct answer, but I take all of them?
So you won't, the system won't get you into a negative territory, if that was what you feared. So the minimum mark that you will always get for these multiple choice questions is 0. Otherwise, well, I could set it up in this way, but it's probably not not too fair. Do note also that there might be, I think this is also important to say, that there might be more than one correct answer. If I give you a path or a graph and I ask name all the nodes of maximal degree, and just list them comma separated, and there are 2 nodes, then you can input 2,3 or 3,2. If there's no instruction that tells you how to input them, then there can be multiple correct answers. Don't worry about this. All correct answers will be counted.
When you say short response question, is that like find the path 8-5-1, or is it actually like written paragraphs? Like what is?
No, so short text will always be along this line, that you have a very clear instruction how to input your answer so that it is treated as a string, but it will not be actual text that you have to write. Further questions? Okay, so then when you submit all and finish, what you will see is finished. No more attempts are allowed, so you're done. You can have a drink or 2 and then just wait for the next day before you get your result. As I said, even when you're finished, please avoid posting any questions on the forum because others obviously might still be working on their test. Okay, so that was this. You had seen 3 example questions that illustrate all the types of questions that you get. They are also indicative of the type of questions that you might get. And I've now prepared an in-class quiz, which is a bit more fun, but also, no, I don't want to do that. But which allows you to play with a few further multiple choice questions. Those of you who have been with me in 9020 in semester 1, they already know the system. Who hasn't, what you have to do is you have to use your mobile, your laptop, or computer to play. If you haven't got one, well, go for it. You have to go to a website that is called Kahoot.it. Oops. You can see that here. So that's the website that you want to go to. And when I start the quiz, then it will generate a pin, and that pin you have to enter. And then the first and most important thing that you have to do is to think of a nickname for yourself, which will then show up in the leaderboard. And as always, there are prizes to win. Now, what will be the prizes for today? Last time before Easter, I had Easter bunnies. Now we are close to the Mid-Autumn Festival. This is why I've got a mooncake. Yes, and it's a very nice mooncake directly from Hong Kong. Now the second prize is this wonderful USB 8 gigabyte CSE wristband. And I've got one of those here as well. Why would you want to wear it as a wristband? Well, the reason to do this is that you don't lose it. USB sticks are easily lost, and you can have this. Now, I don't even know which you would prefer, so the winner will be able to choose either of the 2. And then what I usually have is some European chocolate, and that would be the third prize that I have. Okay, so this is what you are going to play for. And now let's get started. So you go to kahoot.it. And I turn that off. That doesn't really make sense. Okay, so this is what you have to enter. And then, yep. Okay, very good. As I always say, I have very good Chinese friends, and I always show them the Chinese characters and let them translate whatever is shown up here, so be careful. Oh, by the way, what you don't have to do is when you see these questions and the answers in the end, I will put all the questions and all the answers on our course webpage in the end so that everyone who is not watching this video, you can access the questions and answers later. You don't have to take pictures. Eric Martin is here with us as always. Yeah. Invariably, he comes each and every time I have this quiz. Very nice. All right, so is everyone ready? Oh, I like that. Thank you very much. Ready? Anyone not? Okay, so then stop changing your nicknames because I will start in 3, 2, 1, and here we go. Now, the first question is just for you to get used to it. There is no incorrect answer, just so that you see what happens. The questions shows up, then you get some very simple code, and you get 4 different answers. Don't choose just yet. You will see on your mobile or your computer just these 4 different symbols, and you have to press the one that corresponds to the answer that you want to give. Now, in this case, yes, it really is very difficult. But you can even choose the wrong answer. This doesn't count. It's just for you to see how these questions work. All right, once everyone has selected an answer, this would continue. You also see a timer counting down. Very good. Okay, now this question is certainly not indicative of questions that you will get for the mid-session test. And actually these questions, they might touch on topics that will also be covered in the mid-session test, but they are a bit simpler because here you only have a maximum of 2 minutes for every question, whereas in the mid-session test you have 5 minutes. Here also the speed matters. You get more points the faster you are, but you will get 0 points for any wrong answer. Okay, so that was the mock question, the test question. Now you know how it works, and now we start with the real, first real question. Well, there were 0 points, so that was probably very random. But now let's get started. On a CSE machine, how many bytes are needed for a dynamic array of 10 elements of this type? All right, still 50 seconds. A few answers are missing. 30 seconds. If you don't really know, then take best guess. Very rare one. I would have hoped that this was a little better. So remember, there were two integers. Both take 4 bytes. And there was one pointer. And a pointer takes also 4 bytes. So that's 3 times 4 is 12. And an array of 10 elements is 120. Okay, these are things that you should know. Let's see who was fastest. That was very quick. I wonder if that was pure luck or whether you really saw it. There will be other questions. And I don't really expect that anyone is able to answer all questions correctly. So everyone can still win. What is the problem with the following piece of code? That's a tricky question. Now, as I said, I will publish all these questions and their answers on the web page. 30 seconds. $20. Maybe you can exclude some of these answers. And I admit that this is a difficult question, in particular under time pressure. That's a very uniform distribution. If you later look back at the question, memory leak is what happens. You free the outer pointer first, and then you lose access to the inner pointer. So there is allocated memory that you will never be able to free again. But I admit this was a very hard question. Is that the same? I certainly remember that. Okay, let's see. Next question. Still nothing is lost. There will be 7 questions in total. And they won't get easier. This one is a very tricky question. Don't answer too quickly. You want to implement a queue with a singly linked list, and you want to do it in the most efficient way. What is the best you can do? It's also a difficult question because we haven't talked about this. 10 seconds. Take your best guess if you haven't answered yet. 5. Right. That was a mean question because we really didn't talk about this. But there is a way to do it in such a way that both operations are constant. And the trick is you use 2 pointers. You use one pointer to the beginning and another pointer to the end of your linked list. It's still singly linked, but you enter from one side and you take off from the other side. And then you only have to either operate on the head or only on the tail. So you take away from the head and you enter at the tail, and you can do that with 2 pointers. But that was a very mean question, and I think that was more difficult than the questions that you could expect for the mid-session exam. It might be a type of a question that you can have for the final exam, where obviously we don't just have multiple choice questions, but where you are asked to develop algorithms, and maybe we ask you to develop a most efficient way to implement something. And then I would like to see you develop an algorithm that does just what I described. Let's see where we are. The Kiwi is still there. 111 is there also, but here this looks like all 3 questions have been answered correctly. Very good. Now I'm a bit mindful of the time. And this goes to everyone who's listening to the recording. The recording will cut off in 2 minutes. You're not going to miss anything. The only thing that you're going to miss, if you're listening, is to see who is winning that contest. As I said, I will put all the questions and all the answers online, so you can easily see these questions and answers later. And everyone here in this room, if you really have to leave at 5 to 9, then you're most welcome to do this. There's, I believe, 3 more questions, so it might take just a few more minutes. What is the asymptotic time complexity of this algorithm? This might be a bit simpler, but still requires you to think about it.